We're going to go back to section 2.1, which is about tangent lines and velocity. And then we're going to go right into 2.7 and 2.8. And this section is pretty much an introduction to 2.7 and 2.8, which are very important sections having to do with what a derivative is. So let's say we wanted to find the trend in slope at a point on a curve. Well, first of all, some lingo. A tangent line is a straight line that has the same trend and slope at a point on a curve. So if we cared about finding the trend and slope, we could use this tangent line and find the slope of it. Locally, the tangent line only touches at one point. So for this little example I have here, in blue we have point P, and the tangent line is in blue to the black curve that is our function. And so notice that locally here, and I'll erase this in a minute, but kind of to use some highlighting here, we're looking at around the neighborhood of point P, and locally that blue line only touches at point P. It doesn't touch anywhere locally around that. Now it does touch here and it actually crosses, but that's not really in the neighborhood of the point P, so it's okay. So looking at this, pretending I had kind of a scale on here of x and y axis that had equal distance between the tick marks, this looks like it has a slope of maybe about -1. So that would be the trend in the slope at the point P. So I'm going to go to a Wikipedia page about tangent lines because it has a nice demo, if you scroll down, showing the blue curve that is the function, and notice we have a point that is moving from left to right. It's starting on the left here, and the straight line that's being shown is the tangent line at all those points sweeping through the graph. When it has negative slope, it's red. When it has positive slope, it is green, and then where it has a slope of 0, it turns black. So this is just to get you comfortable with what the tangent line is, and I would expect you to be able to sketch what a tangent line is at a particular point on a graph, just to kind of estimate what that would look like. I've included the link here. Oh, or maybe not, I thought I did. And so you can just look up wiki tangent, and if you Google it, you'll get it. So example 1 says draw an approximate tangent line to y equals f of x and find its slope for the point at 3, 1. So I did a little bit of the legwork here, and we have the black curve. We're trying to find the tangent line at x equals 3. So I drew it ahead of time so it would look pretty good. Notice that it has the trend and slope at x equals 3. It's only touching locally in one point at x equals 3. And if I wanted to approximate the slope of that, I could just use the rise over run. I could find 2 points on the blue line and use a slope equation for that. It really doesn't matter. One of those methods, I just chose to just do rise over run. I made my right triangle underneath, and then I estimated the rise as the change in y, or the dimension, the height of the triangle. It's about 5.5 because the line falls from left to right. It's negative slope overall. And then the run is the base of the triangle, and that's about 1.5. So if you divide that out, you get about -3.7. So I put an approximation symbol here because, this could be a little off. We're just trying to graphically estimate the slope of that tangent line. So this is a good way to estimate the slope of a tangent line. However, we're going to do another estimate of the tangent line, which seems a bit silly, and it's a lot of work, but it's actually something that is the foundation for what we're going to do in 2.7 and 2.8, and so we really need to look at it from this perspective. So here we go. Another way to estimate the slope of a tangent line at a point is to use the idea of a limit. and calculating slopes of lines that include the point P and points getting closer and closer to point P. So when you are doing this and you're picking points that are close to point P and P itself and calculating the slope of those lines are called secant lines. And one thing I forgot to mention with the tangent line is that's a totally different thing from the function of tangent. Same deal here for secant lines. This is not related at all to the function secant from trigonometry. The reason the names are similar is because the Latin comes from the same thing. The secant base word means to cut or something like that, which makes more sense. Now, how that applies to the trigonometric function, I'm not really sure. But, you know, it's all coming from these Latin words. So anyway, don't get confused there. Alright, so this is something that you're going to have to do on the homework, and also something that we'll do in class, a similar example. Consider the function f of x equals x minus x squared, and the point P is at 1.5, comma, negative 0.75. And I included the graph here, so notice the point P is indicated there. Okay, first thing, graph the secant lines passing through P and Q for x equals 1 and 1.25. I just realized we're probably going to run out of time on this recording, so I'm going to stop here, and then the next recording will pick up with this example so I can make sure we finish it.